Hello, this is my last series in my mini series on characteristic functions, moment generating functions, factorial functions, and this is just some applications using the characteristic functions. These would be much more difficult without using characteristic functions or moment generating functions in many of these cases. So let's just jump right in. So here we're going to let the xi's be random variables, binomial with nj, and a common p, common probability. And we want to show that the distribution of this sum is again binomial, where n is the sum of the n's and the p is the common p. Well, this here is the moment generating function for a binomial random variable, and you can look in my video titled Generating Functions for a Binomial Distribution. And then the next property here, in pretty much every one of these, you'll have to refer back to the characteristic function of x. It's a video titled that. Basically, we want to find the characteristic function of x, which is this sum. So that's equivalent to the sum. But since they're IID, that's the same as the product of the moment generating functions. So we can plug in the moment generating functions for here, and then the product of these numbers is you add the exponents, which becomes this. And this again is a binomial distribution. And so since there's a one-to-one correspondence between characteristic functions and distribution functions of a random variable, then we know that the variable x has a binomial distribution. Next example, let xj be IID, independent, identically distributed random variables, Poisson lambda j. We want to show that the sum of these Poisson distributions is again Poisson, where the lambda parameter is the sum of the lambda j's of our random variables. Well, this here is the characteristic function of a Poisson distribution, again, reference to this video. So now we want to find the characteristic function of x and show that it again is of this form. So here we have x, which is the sum, which since they're IID, it's the product of each individual characteristic function, and they're all of the same. This we plug it in. Well, e to this, multiplied k times, you add the exponents. So these lambda j's become this, and then this is a coefficient in front of this term, which you end up adding those, which is this. And then if you think of this as lambda and that's lambda, then it equals this, and this is of the form of a Poisson distribution. So the distribution of x is Poisson. Now let's let xj be IID random variables with the normal, mean, mu j, variance, sigma squared j. We want to show that this linear combination is again normal, and that's the sum of cj xj. Where mu, the mean of this linear combination is this, cj mu j, and sigma squared is the sum of the cj squared, sigma j squared. Well, the moment generating function, or the characteristic function for a normal distribution is this. Again, I'm going to refer to this video to derive that. Now we need to show that this linear combination is of this form. So we start. So phi of x, well, that's the sum, and they're IID, so that ends up being the product of these individual characteristic functions. So we plug in this for each one of those, and we get this. But this is e, and it's a product, so you end up adding the exponents. So there's a common term, there's going to be k of these. There's going to be a common term here. You can factor it out, and ends up being the sum of those, which we called sigma squared. And then here, there's a IT common. So when you factor it out of this big product, you end up with the sum of Cj mu j, which we called mu. And this is of the form of a normal distribution. So this sum, linear combination of normal random variables, is again normal. So let's let xj be IID random variables chi-squared with degrees of freedom rj. We want to show that this sum is again chi-squared with r degrees of freedom, where r is the sum of these rj's. So now this is the characteristic function of a chi-squared distribution. And note that I'm referring you to, again, the generated functions for a gamma distribution. And that's because a chi-squared is a specific case of a gamma distribution. And that derivation's in there at the end of the video. So then we need to show that this sum is again of this form of a chi-squared. So we plug in, we find the characteristic function of x, which is this sum, and their IID. So it's the product, and then we plug in those here, and there's rj of them, and so we add, since it's the like base and we're adding exponents, it just becomes r, and this is again the form of a chi-squared distribution. So this sum is again chi-squared. Now here is a Cosi distribution, and it's pretty interesting. It's one of the few distributions that doesn't have a mean. So the central limit theorem doesn't apply. You can add up a bunch of Cosis and never get, it doesn't limit to a standard normal distribution. So what does it limit to maybe? Well, let's assume we have xj. Let xj be IID random variables Cosi, the standard Cosi distribution. And we want to look at the sample mean. We want to show that it's again a Cosi distribution. So this would be tough without the characteristic functions. So this is the characteristic function for a Cosi distribution, and again I derive it in here. Actually, I reference it, and then this video references another video I have that derives that. So you have to go back twice. But so this is the characteristic function of a Cosi, standard Cosi. So if we look at x bar, that's k times the sum of xij. And then the property says, since they're IID but all times a constant k, you take the product, but you take that constant and take it times t. So then we take this in here, but we take it times 1 over kt. So what that means is that we have the product, and we're going to plug this in, but we're plugging 1 over k times t in here. Well, now there are k of these, so we raise it to the kth power. But remember, this is a power, so this is e to a power, so we can just take it in, right? And k is a positive number, so it can actually come out of the absolute value. K over k is 1, so we get this back. And so the mean of Cosi random variables is again Cosi. Okay, well that's all I have for this video. I think I'm going to start another series on limiting distributions and inequalities used in statistics or something like that. If you like this video, please like it and subscribe so you don't miss the next one. Thanks, bye.